cover, the knife wedge, the disc, and the magazine holder. And on the next slide is the housing cover guide, which is the main foundation of the assembly, and all the parts attached to that. See, the knife block attaches to the gate cover, which swings in and stops the cards from falling out. And the magazine block sits on top of that. The cards will fall onto the disc, as seen here. Here it is in all its functionality. Yep, you see the lids fall down through the cover guide, and the lids fall into the slots on the disc, one by one. That's how it's supposed to be. The main problem here is that the lids have variability, different thicknesses or warping, different shapes and all that. What happens is they have to change their knife block out every so often. The new stack of lids comes in, and it's very detrimental and stops their entire process from working. You have to go in, take apart the whole machine, and replace the knife block. They went into a adjustable knife. Even then, that was still a not so helpful process, because they have to stop the machine, manually adjust it, turn the machine back on. If it doesn't work right, or one lid going at a time, and stop the whole process. It's an assembly line. You stop one part of it, it's not going to function. And we are here to streamline it, which is here in our problem statement. We're here to reduce the manual adjustments needed, like taking apart the whole machine to change the knife height, which limits how many lids go through, and to improve the reliability of the system, as well as minimize total downtime, as it's easier adjustability, much simpler. Nothing has to get taken apart. It's just on, change the height of the knife, change the.
What's the knife? I don't understand what is the knife cutting these out?
Oh, sorry. So the knife is this yellow block.
Okay.
And it goes to different heights in our new design.
It acts like a wedge. They call it a knife, but all the knife block does, it wedges the lids, so all of them doesn't go through when the disc is moved around.
So it's ensuring only one lid at a time is dispensed.
Yes, sir.
Okay.
Yes.
Pretty sure none of us understand the process yet. Anybody else understand the process yet? I'm sorry to stop you in the middle, but none of us understand what you're doing yet. So,
Yeah.
so you're gonna have to spend a minute here to explain it, because otherwise we're not gonna understand anything you're talking about. So.
Do you want me?
Go slower.
Do you want me to take
The
it?
lids go through the stack here.
Right.
They fall down to the bottom into a pit with a disc. And the knife.
What is the knife there?
It's deep seated below the gate cover.
Can you point?
It's hidden in
Can you just pause the thing and point stuff out to us, because we don't know what you're talking about right now.
The laser pointer on
So,
So the gate cover is what? The red thing?
right, this is the gate cover.
Okay.
The knife is attached on the other side of it.
Okay.
And this is with the adjustable version.
Okay.
This cutout space right here,
Right.
that is their new knife that is adjustable via
Okay.
a screwdriver. Goes up and down, and sometimes a lid will go through at one by one, or none, or two.
Okay.
If zero go through.
So it's like moving in or out, or to separate the lids?
It just moves up and down.
Okay.
And that is enough to change how many lids go through.
Okay. It's basically peeling one lid off at a time.
Yes, sir.
And these are the lids?
Mm-hmm.
Okay.
They,
As the disc rotates, it just drags the cable with it.
Okay.
Yeah.
So this is basically holding the lid above the one that they want from falling out.
Mhm.
Right, and it's just gravity driven,
Okay,
lids fall through.
all right.
Yep, sorry. They do have a vacuum seal on the bottom lid to easily track it. We don't have a vacuum seal on our prototype side.
Okay. Right, and because they gotta adjust it all the time, it holds everything up.
Mhm.
Okay, all right, I'm ready now.
So again, we're
Okay.
here to remedy all those stoppages and losses in their assembly process. What they wanted from us is exactly that. Our problem statement is a exact, or a direct answer to what they're asking for: decrease losses or waste, and increase reliability and efficiency. The school did require a little more from us, and it was to create a engineering solution, that being a iterative or a design that can be made changes of and increase the functionality, as well as having a measurable result, that being the efficiency of the lids or the ability to make a knife block move up and down at a precise measurement. Here's our work breakdown. This just shows how we diversified the work. It is color coded to help see what all the varying objectives we went through throughout the year process of finishing up this project. Overall, it came out to one person starting, say, 3D modeling or designing, and the others coming through, giving their inputs and finishing out that part of the task. We started with designing and planning, then simulating analysis, as well as going into 3D modeling, eventually building the prototype as you see here. And once we had that, we could do physical testing, assembling the prototype.
How's the ridge system different from the knife system?
The ridge is the top stack. The knife is just the block that goes up and down.
Okay.
So two different parts that we designed to assist the efficiency of the assembly process. And all things were reviewed by MedTech multiple times. We had to redesign a lot of things. They gave us a lot of critiques and inputs about how to make something more manufacturable and more efficient.
So with this project, we had to set up some potential design options overall. Here are some of the ones that was suggested overall that we did talk about. It was mostly vague. They all have been denied for multiple reasons. We had an environmental chamber design where we would just make an environmental chamber and set up for all the lids to be uniform in a uniform temperature, uniform humidity, and generally the same. The problem with that, it would be too costly to do that for every single lid in the facility and just takes up too much room. We thought of adjusting the knife with a ratchet system, a ratchet and ball system, and that was just way too manual, and we really couldn't focus on what Angelo State wanted us to do fully with that design. We also thought of spraying air hose within the lids to help push it through, but that was just not really effective or feasible. We thought of using a door plate to push down lids, so it's easier just for a vacuum to pick up one, but that one was just not the best. We thought of using a roller like a cash counter to send out one at a time, but problems with spacing and electricity wouldn't allow that one, and we thought of roughing their old knife tip, but that could damage the lids. the reason why we talked about all of this is to lead to what we ended with for our design. So before, we had this design over here, which Ethicom MedTech, Johnson & Johnson MedTech was using, was a very physical design in which if there was a problem, they would have to physically take apart the system and put it back together. To a point where we set up a very automatic and less hands-on system, semi-automatic, where one, we would implement guide ridges. These guide ridges would ruffle the lids and make them flow better so they're not stuck together, which is one of the big problems with it. And the second option is to have a stepper motor, which is controlled away from the system fully. Through that, it would not be, you don't need to take apart the entire system to work on it. So with that, we ended with this final design. It took us a lot of trial and error to reach this part, and we spent a lot of this semester redesigning it all to fit this part. We color coded everything so it's easy to follow. If you have any questions during this, feel free to open. We marked the motor, bearings, and fasteners with black, red for our cover guide base, which is the base that the entire thing is built on. We have brown for a mount in which we attach our motor. Green is our gearbox, and blue is our guide ridges, with grays being the disc plate. Our final design is a front, side, and top view. We had a very short, small area that we could work with, reaching to a point where we're at a height of 9.25 inches with a length of 5.928 and a width of 0.377.
Here's the assembly of just the guide ridges. It is made of 4 different components. The block at the bottom here, which screws into the bottom of these walls. Both are different because there's a adjustment for the ridges to do their ladder rippling, as well as a hole cutout for the gear set to maneuver through. Then there's these guide rods that stop the lids from sliding out, the open air. And then there's a magazine cap, screws into the top of the walls, holds everything tightly together. It's just one unit, as you can see. Everything is made of aluminum 6061. It's a common material used by MedTech.
Anodized.
Yep. Here's the geometry for that. It will catch on one ledge, trickle down to the other side, and keep doing that until it reaches the bottom. That's just geometry.
So we're focusing from there to our ridges to our gearbox. We set up a gearbox with multiple different parts. The main parts over here that's focusing on is we have a motor, we have a Nemio 17 stepper motor that has a holding torque of 3.54 pounds per inch with a 1.8 step angle for 200 steps per revolution. We set up a gearbox housing with a width of 3.93 inches, a length of 5 inches, and a height of 2 inches. We did 2 separate types of bearings for this system. We did a TB50 thrust bearing and a R10 R series ball bearing. The thrust bearing is this little block right here, and the other bearing cannot be seen, but it's underneath the worm gear right here. And lastly, we have our lead screw, which feeds into our knife block, which goes to this over here. Over here, we have lead to our worm gear and our worm. This is our worm, and this is our worm gear, sorry. But overall, it's 15 degree pressure angle system with the lead angle being 3.05 degrees and the face width of the worm being 0.87 and the face width of the worm gear 0.39. The most important thing of this is it's a 50-to-1 ratio. And it's made out of two materials, steel and a manganese, aluminum, brass, lead alloy. I cannot say the chemical formula for that, but you know. The main important thing of this worm gear is it's set up in which the box over here is able to turn. It's held up by the sides, and the worm could move up or down by 0.001 inches by each revolution. And for that, we calculated the tangential load output to, which is 44.7 pounds and 76.5 pounds per inch. I apologize for that mistake. We have an efficiency of 43% with our total system, with a bending stress of 10.8 KSI, a surface contact stress of 3.9, and a surface safety factor 7.7. We have a power loss of 0.0192 horsepower. We have multiple different components within this, and it's mostly the lid for the gearbox, the motor mount which attaches the motor, and the cover guide base. Through all of this, to make this model, we had two different opportunities with it. We attempted to have it manufactured using aluminum 6061 and stainless steel. But due to budget constraints and last minute changes, we had to change our prototype from a aluminum and based model to a 3D printed model with a lower budget. The cost difference is over half, where the potential final product would be around $1,000, while the 3D printed only spent around $400, and after that cost was just filament. Our constructed design could be seen here. It's many different parts to make this together. They are as shown as before, but it's our gearbox case where that bearing I was telling you about that we've seen is right there. The lid, the worm gear, the worm, knife block, the lead screw, the gate cover, and the housing cover base. The magazine could be seen here, where it's connected through a rod, and the cap, and the motor mount, and the pin. There are pins attached to the sides of the housing cover base. The prototype could be seen through here, constructed fully. We did do circuiting that was not the best prepared, but it was a really good learning experience. And through that, we connected a 12-volt power supply to the system through here, which feeds into a circuit that touches a chip and manipulates the stepper motor up or down when controlled with a Arduino board and our Arduino joystick. This is a fully constructed view, nice and pretty for all of you, of the stepper motor view in action. So to fully analyze this, we had to compute the amount of distance that the knife block would go. In which, as the gear turns, and the knife block there is constructed by the x-axis and the z. It's forced to go up or down as the gear turns. We calculated that it would turn 0.00112 inches per revolution. But with experimentals of done multiple times of 2,000 revolutions divided, we got our final distance divided by that. We got around 0.012 inches per revolution. Do note that can be possibly wrong due to factors like this is not as set up with the correct materials as we calculated based off of. It's not set up exactly in the scenario in which it would be attached to a roof of plastic and so forth. We achieved a 7.9% error based off of our testing though. Here you go, Michael. I'll cut off the reason why we're doing the simulation first.
Yep. Here's the simulation of the guide ridges. Paper will fall through, ladder down the ridge walls slowly to the bottom. Due to some geometry constraints in modeling, it got finicky and got caught on themselves. Now, we did a lot of testing with the actual model, which came out to a major problem. That meaning that everything was designed in very tight tolerances, near exact, or at least within plus or minus 1/100th of an inch by professional fabrications at the Johnson & Johnson Manufacturing Center. On 3D printing them, our tolerances became probably within 1/10 of an inch, which means the cards do not go through unless forced, in which case you have to gently lower them down into the cavity here at the bottom. Even then, it's not very precise. There's a lot of manual lathing at the labs to even get all this fit together and functioning. And same, like you were saying before, this isn't the exact design we were going for originally with all aluminum or steel components. Going with 3D printed components, the blocks are difficult to fit together. Best we can do with the resource we had. But it came out to the garbage is not fully functioning.
Got this. Feel free to pause it right here. So this is a video of our prototype in action. We could actually run it right now. It's not too bad, but it's the main thing with this system is we had to set up an emergency switch, which we were told fairly last minute about, and a power system that wasn't powered by batteries. It was a primarily designed to represent the concept of our thing. So you can continue the video now. Mike. The knife block is currently set up so it could allow only one through. Although the block over here is not really steady or balanced. It allows you to turn the wheel to represent the knife moving, not the knife, the disc moving and allowing one by. We don't have the vacuum system to pick up the lids, but we can represent the knife moving up or down with a little motor over here. Once we finish it, we set it up to shut down with the emergency power switch. Here you go, sir.
This lies social, economic, global, and cultural factor. So we consider the social factor is increasing social production, improve access to medical supplies, and better ability to support hospital and clinic and other healthcare and reduce defect lead to more consistent delivery of medical tools. Next, economic factor is improve efficiency, increases production output, and lower downtime, and material rest is result in cost savings, and enhancing the cover load assembly boost our profitability and manufacturer value. And next, global factor is higher efficiency develop the global material and medical supply chain, and reducing reject lead, decreasing and natural waste, contributing to environmental sustainability, and reduce material waste arise with global manufacturing trend. And last one is cultural factor. Cultural factor is minimum for this project because tool production is a technical process. So the safety analysis. So we reference for based on ISO 12100 guideline. So we focus on gear one gear part and lead screw, night rope. So patches is moving knife, and moving knife is cutting pinches, and one gear and trapping regions, and lead screw is backlash of extended drop. And risk analysis. So risk analysis standard is based on the NASA risk guideline. So we make this table design machine risk analysis. So we put the cutting and pinch and trapping regions and lead screw backlash and unexpected drop, and it likelihood is so oral part is D, and subsidy is 2, and level is low. And this table is design team risk analysis. So first, we we make the CAD file and then print 3D printing. So 3D printing part is so core and other part is fit. And so we change dimension and geometry errors and communication gap and limited access to lab equipment and assembly step issue. So assembly step issue is case is shape edge and rotating part. And likelihood is repeat CAD file is D, and 3D printing failure is D, communication gap is C, and limited access to lab requirements C, assembly step is D, and severity is first one is 3, or of 3, and we put the impact medium.
Overall, this project was capstone project overall was a very helpful experience. Even though this project has gone through falls and downfalls, it was a very active experience. Through this project, we struggled a lot with talking to our client and understanding what our client needed and getting resources from our client, but we really do appreciate them throughout their help. We did got a change, our client did change a bit in the second semester, which resulted in us redoing all of our work in the first semester in the second semester, leading to a whole new design from the first. That is similar to the current one, but similar to the original one, but is entirely new process and new design. We also learned that our whole process could have been streamlined to one additional item from our clients within our last design meeting with them, which leads us to, if any future capstones would work on this project, they could use a piston or a similar item. We were originally told not to focus on any of those items, but that could be a whole different view of it. Redesigning our guide bridges to be relying less on tolerances and have more time with an active model that Johnson & Johnson MedTech would be happy with to manufacture. Overall, their help was a really great outlook into the engineering world for the positives and negatives that it went along with it. We would like to thank these wonderful people. Two of them aren't here, but you know, maybe Dr. Hawk, Dr. Garcia, Dr. Kitch, David, or Dr. Wallace. We also like to thank the wonderful SEAL Team 5 for their active help within our project and understanding Epicon standards when we couldn't get in contact. We also have fellow acknowledgements with our new direct contact for Epicon. We do like to thank Romero, Tom, Hager, Kenzie, who's been with us for the whole project and helped us get through with it. Cody Friendress, who taught us the active style of how Epicon likes their files, how they like them made. Luke Anderson in active help with construction and printing of these items. Ricardo with help with electrical. Chad and Dristy for being there in our first semester. And the milestones. We do have our references afterwards, but that's the end. Yes, sir.
a question. Typically, in a manufacturing environment, you measure parts per minute. Did y'all measure the parts per minute with the current, and then what the output would be, the parts per minute under a new design?
No, sir. We were basing off this design that it would work as it would currently. Our design is to reduce downtime. So if there's any downtime at all with the project, they don't have to take apart the entire assembly just to change one screw, reassemble it and test it. They could just turn on very noisy box and move it up or down.
So did you measure the downtime, how much it was and how much it would be? The new
No, sir.
design? Okay.
We can speak on the amount of downtime. That was out of maybe 12 visits to their facility. Their machine wasn't broken one out of those 12 times. So they were in desperate need of some kind of fix, and we had provided one solution for them.
So can you repeat, you said sort of, you visited 12 times, it was down every time? Is that what you just said?
Right.
Okay, I misunderstood you the first time. I heard the opposite.
12 times, it's only down one. No.
So on a previous slide, y'all had like an 8% error on something. What did that error represent?
Should be the difference in the analysis and the actual functioning.
It's basically, we had, in a perfect world, in a perfect system, in which everything's together, based off of the electrical model, it should only move down by 0.001112 inches per revolution. But based off our testing, we got 0.001, about 0.0012.
And what is the thickness of the lead?
0.002 inches, if I'm correct. It could get up to 0.003.
So even with that error, you are between tolerance?
Mm-hmm.
Okay.
All they asked for was if it was gonna be adjusted slowly, to have it be adjusted by 0.001 of an inch.
It is quite slow. It takes 15 minutes to move 1¼ inch. Oh, like that's going from all the way up to all the way down.
Yeah, but they're only gonna be adjusting it like, what is it, 2/1000th of an inch at a time,
Yeah.
right?
So it's a very,
So how do you know how much is moving? Do you know? With the controller that you have?
not exactly, if, we had the resources with, we did not really know too much of what electrical requirements we would need when we first designed it. And it was one of our last design items we focused on. We originally focused on moving it up or down very smallly, but, if that would be redone, we would add a screen over there that would tell you, its distance from the bottom, calculated based off of
So,
that.
okay, so right now what you will do is like,
It's
okay,
eyeball.
like
Eyeball it.
moving, yeah,
Yeah.
like, okay.
Yeah.
Can you show your work breakdown structure again? Way back at the beginning.
Oh, all the way to.
Yeah, the little work breakdown structure, yeah.
Oh, no.
Yeah.
So who did you
So I-
delegate to what?
Yeah.
Like who was team lead, who was design lead, who was manufacturing lead, like how did y'all delegate that?
I was team lead, Michael was, design lead for the Rich Systems, and Leon Jen was
So the,
based on, of the lead screw.
so is the rich system the thing that holds a cassette of?
Yes, sir.
Okay. So I got all the way through, yeah, I finally figured that out at the end of the presentation. I mean, just a little feedback.
Sorry.
Was that, you know, so I, when you showed this, I said, okay, you got, I'm not sure what the middle part is, it's the integration, I guess, but you got a rich system and you got an ice system, great. I did not really understand
The
What was
rich.
what?
that, until the end of the presentation, you know, maybe last, very, near the end of the presentation, just as a feedback. So what is the purpose of the ridge system? What would you describe as the purpose of the ridge system? Mike?
When we.
Wait, he's the ridge system lead, let him talk.
It's to riffle the cards in a automated state.
Man, I wish you'd said that at the beginning. Cause, I mean, so it's basically to set these up so they're separated enough that you can actually hopefully get one at a time, right?
They're not
So it's
sticking to
just
shot.
packed in
Yeah,
at the bottom.
I mean, I don't know how, I don't have a good way to say that, but what you just said was better than anything else. And that's the best description I heard. I understand, when you said that just now, I understand it. And I'll just, again, as feedback, that's the first time I really understood what the purpose of the ridge system is. I was sort of intuiting what it was, but,
Spacing out the loops.
did you do a dry run presentation?
We do.
Yes.
Did you get feedback? I'm just asking, 'cause I mean,
Oh,
I
we did
obviously
it
wasn't
too.
there, else I would've known.
We didn't have people to listen, so we went through it multiple times and redid a lot of these
Okay.
slides.
It's a very, it's complicated to demonstrate this, right? I mean, it's also, it's very difficult, but if you can't somehow get us there, I don't know, I'll speak for myself, I spent 80% of the thing trying to understand what it was you were doing.
Mhm.
And so, it's really hard for me to evaluate the overall thing, because it was just really hard for me to understand how the system worked, what it was you were doing, where the big holdups were. So I don't know how you do that with, you know, I don't have the like magic wand, especially when you're chewing a mechanical system. I mean, I spent a lot of time doing this with teaching stuff, like trying to describe things that are really hard to visualize, right? So I can appreciate that, but I don't think you can do it with stills.
So currently, the display is manual, correct?
Yeah.
Do you think with enough time and resources, you could have made that automated, or this is for Mr. Economical Factors, did you deem that to be out of the budget, out of your pricing, to kind of make that automated?
I'm so sorry. Why would we?
So in your concept, do you think they are going to implement this?
No, sir. They told us on our last meeting, exactly at our last technical meeting, how they could redo this better, with one part. And that we kind of learned that the gearbox system was really redundant in that way.
So overall, so for each of you, what is the biggest takeaway you learned? This is supposed to be a learning exercise, right?
Mhm.
The goal is not to produce a functional system. The goal is was to learn something. So what's the biggest thing that you learned, Myogen?
I think I learned about I'm interested in gearbox and motor, so I designed the lead screw. So I focus on lead screw, rotating, and I learned
What was your main takeaway?
Yeah, yeah. What was the number one thing you learned out of the whole thing?
that is no problem.
Michael?
Think on definitely how a engineer works in their job at a big company, or maybe a more industrial factory setting.
So what is that one thing that you learned about them that's like super, you got it?
I wouldn't mind working a job like that. It's a lot of what we do, designing, iterating, then the various process after all that, along with more interested in the manufacturing part, getting from design to manufacture to the assembly line, all that.
For me, it's just where to pick my battles overall with this project. The biggest thing was I struggle a lot with leading and distributing with that, as I was the point of contact with the group. I was the one who generalized a lot of the meetings and the one who tried to set up achievable goals for everyone. The big thing of that would be, what should I do? Is this reasonable for me and my group? And who excels at what is the biggest thing I've learned to face.
Good, thank you all very much.
Thank you.
Thank you.
We're gonna have to take the living, give it to police.
I guess I'll collect.
Got a dean straggling over.
Yeah, I saw that. I'm gonna pigeonhole. I got a question for you. Yeah, just fair warning, so if you wanna get out fast.
I got my eye on the exit.
Hey, Dr. Hawk, how are you doing? Good to see you. Hey, Dr. Kitch.
Hey, how we doing? Good to see you. How you doing?
Hey, Garrett. How we doing? Good to see you. Hey.
Did I see these pictures?
Oh, yeah, you want?
Yeah, that's like a secret stuff.
Souvenir.
Yeah, you can't.
Patty ran through.
Perfect.
Smooth.
Wait for him.
Does anyone have these cards with them?
Milo just picked them up. So those are top secret, you can't let those out?
J&J property, we got there's some.
These guys are like security conscious, I don't get it.
We got
That
one
was
right here.
a lot of, well, there's a lot of sweat going on having an unofficial NDA.
Yeah, I know, yeah. Yeah, their lawyer told her there wouldn't even be a problem doing the NDA a year ago. You still don't have one, right?
We spent almost a whole semester fighting on this. Now we're gonna move to our third and final presentation. I'll hand over to the.
Oh, we turned it off.
Oh, yeah, we turned it off.
Why is it not?